You ever look at a diamond and wonder, how is it so hard? Or why is metal so shiny? And the big one, why does your salad dressing always separate? Well, the answer to all of this, believe it or not, comes down to the secret social lives of atoms. It's all about how they connect, which we call chemical bonds. So let's get into it. All right, so today we're going to solve one of chemistry's most famous and honestly most common mysteries. You've seen this a million times in your own kitchen. Why on earth won't oil and water mix? I mean, they're both liquids, right? What's the deal? Yep, it's a total classic standoff. But to really get what's going on, we've got to zoom way, way in, down to the atomic level, because that's where the real action is. It all comes down to the tiny electrons and how different atoms decide to handle them when they form relationships. And it turns out, atoms basically have three main relationship strategies. Think of it like this. They can either give and take, kind of like a heist, they can share, or they can just throw all their stuff together and live in a big commune. And each of these strategies creates a totally different kind of bond, with completely different results for us in the real world. Okay, let's start with the most dramatic one of all, the electron heist. This is what we call an ionic bond, and yeah, it's a total story of a giver and a taker. So here's the key thing to remember about ionic bonds. There is no sharing. It is a complete and total transfer. One atom straight up gives away an electron and another one grabs it. It's a one and done deal. And in this little drama, you've got two main players. You've got your metal atoms. They're the givers. They're totally fine with losing an electron. And then you have the nonmetals. They're the takers. They are more than happy to snatch that electron up. So what happens after the heist? Well, now the atoms aren't neutral anymore. The metal atom, because it lost a negative electron, is now positively charged. We call that a cation. The nonmetal, which gained that electron, is now negatively charged, an anion. And what do we all know about opposites? They attract. And that powerful magnetic-like pull, that is the ionic bond. And this super strong positive and negative attraction just locks these ions into place. They form this incredibly organized, tightly packed structure. We call it a crystal lattice. And the perfect example, just think of table salt, sodium chloride. That's exactly what's going on inside every single one of those little crystals. But you know, there's a catch to being so rigid and organized. If you hit a salt crystal, just give it a good whack. You can actually knock the layers out of alignment. And all of a sudden, you have positive ions right next to other positive ions and negatives next to negatives. They instantly repel each other with huge force and, crack, the whole thing shatters. It's the perfect explanation for why something so strong can also be so brittle. Okay, so that's the whole give and take heist story. But what if atoms aren't into that kind of drama? What if they rather just cooperate? Well, that brings us to our second strategy, sharing. This is the covalent bond. Right. So instead of all the drama of stealing, a covalent bond is way more like a partnership. It's all about sharing pairs of electrons, usually between two non-metal atoms, and it's that sharing that literally holds them together, creating a little self-contained unit we call a molecule. Let's take hydrogen chloride, for example. Hydrogen has one electron it can share, and chlorine has an empty spot just waiting for one, so they just decide to share a pair. That way, both atoms get to feel like their outer shell is full and stable. It's a total win-win, and it creates a nice, stable molecule. And you can really see how this difference in strategy leads to totally different properties. On one hand, you have the ionic compounds. With that strong crystal lattice, they're usually hard, brittle solids, and you need a ton of heat to melt them. Then you've got the covalent compounds, the molecules. They're often liquids or even gases at room temperature, with way, way lower melting points. All right, so we've covered giving and taking, and we've covered sharing. But there's a third way to do things. Metals. Well, metals play by their own set of rules. Their unique way of bonding is what makes them, well, metallic. So welcome to the atomic commune. So picture this. In a chunk of metal, none of the atoms are really possessive about their outer electrons. Instead, they all just kind of donate them to a big collective pool. This creates what scientists call a sea of electrons that can just flow freely all around these positively charged metal ions. It's not about heists or one-on-one sharing. It's a what's mine is yours kind of deal. Everybody's electrons belong to everybody. And this sea of electrons idea, it's basically the secret sauce that explains everything we know about metals. It's why you can bend them. They're malleable, because the atoms can just slide past each other in that electron sea without breaking the whole thing.
It's why they're conductive. That sea of electrons is literally free to move and carry an electric current. And yeah, it's even why they're shiny. Those free-flowing electrons are great at bouncing back light.
Okay, giving, sharing, and living in a commune. We've got the three main strategies down. We have the tools we need, so it's time to go back and finally solve our oil and water mystery. So remember how we said covalent bonds are all about sharing? Well, there's a little twist. Just like in real life, sharing isn't always perfectly 50-50. So what happens when one atom in the partnership is a little greedier and pulls on those shared electrons more than the other? Well, that's when you get what we call a polar bond. The atom with the stronger pull, it's a property we call electronegativity. It kind of hogs the electrons, pulling them closer. This makes that end of the bond a little bit negative, and the other end, the one that's losing the electrons, becomes a little bit positive. So now your bond has two poles, a positive and a negative one, almost like a teeny tiny magnet.
But here's where it gets really interesting. For a whole molecule to be polar, it's not just about the bonds, it's also about the molecule's shape. Water is the perfect example. Because it has that famous bent shape, the poles don't cancel out. It has a definite negative side and a definite positive side. It is a very polar molecule. Now look at carbon dioxide. It's a straight line. The two poles are in opposite directions, so they perfectly cancel each other out. The molecule as a whole is nonpolar.
And there it is. That's the answer to our big mystery. Water, because of that bent shape, is superpolar. It's basically covered in these little positive and negative patches. Oil, on the other hand, is made of these long chains of carbon and hydrogen that share their electrons very, very fairly. So oil is completely nonpolar. This all comes down to one of the golden rules of chemistry, and it's actually super simple. Like dissolves like. All it means is that polar things love to mix with other polar things, and nonpolar things, they're happy to mix with other nonpolar things. So what's really happening when you try to mix them? Well, all those polar water molecules are really, really attracted to each other's positive and negative ends. They all stick together like a super tight-knit click, and they just exclude the nonpolar oil molecules. There's no room for them. So the oil gets pushed out and ends up floating on top. It's not really that they hate each other, it's just that the water molecules like hanging out with each other so much more. So when you think about it, from the salt on your fries, to the metal in your phone, to the water in your glass, everything comes down to these atomic relationships. So the next time you see that salad dressing separating in the bottle, I want you to think about it. Where else in the world around you do you see these stories playing out? The givers, the sharers, and this whole idea of atomic exclusivity.